Hello and welcome again. This is another video on polynomial functions of higher degrees. Today we talk about real zeros of polynomial and multiplicity. This is the problem proposed for this video. So we have three questions related to this graph. Determine the least possible degree of end behavior for the graph. Locate the zeros and then multiplicity. Assume all the zeros are integral, that means they're integers, and then create a function that fits the graph and the given point. This is the given point, 2, negative 128. So we start with part A. First, we have to notice that the degree of the polynomial for this graph must be even. We know this from the end behavior of the graph. Okay. So this is our end behavior. This is an example we have seen in the class, an activity for end behavior and odd or even polynomials. For example, this graph is for odd degree and a positive leading coefficient. Because of the end behavior, it comes from minus infinity to plus infinity. The other one is even degree. Same, because of the end behavior here, it goes to plus infinity for y in both cases. Okay. On the left, on the right. This one is even degree with leading coefficient negative because it goes the same direction. The y's go the same direction to minus infinity. Okay, and facing down, opening down. That's why a is negative. And this one is odd degree. Okay, coming from plus infinity, going down to minus infinity. Okay, and because of this direction, a is negative. So we have two types of functions. Odd, as you can see, the odds and the even. Okay, we go to see another student. Here is another answer. Odd degree and even degrees. We have two types. Okay, let's go back to the question. So this is the end behavior. So as you can see, the two branches, they go up with y going to plus infinity. Okay. And that's the end behavior of your graph. So what is this end behavior? Now, to find the end behavior, we just express it using infinity. When x is in infinity plus y is in infinity. This is my point with coordinates x. This is your x for any point on the graph. When it goes to plus infinity, the point goes up. Okay, so when x goes to plus infinity on this side, goes to the right, y, the coordinate y, which is of x, because the point goes up, the coordinates y goes to plus infinity. Okay, yes, that's for this branch, y goes to plus infinity when x goes to minus infinity. For the second branch, okay, this is my point with coordinate x. Here the x goes to minus infinity as the point goes up in to the end behavior. So x goes to minus infinity. Y, when x goes to minus, y goes to plus infinity. It goes up. As you can see, the branch is going up, so the y is going up to plus infinity. So this is how we express the end behavior. We can express it as well using this notation. We call it the limit notation. So limit of y is plus infinity when x is in plus infinity. Same as this, same. It's just an expression using the limit notation. And limit of y when x is in minus infinity, that's the second case, second branch of the graph, y is in plus infinity. This is how we express the end behavior. Okay. That's it. We finished this part. Okay. So the degree of the polynomial must be even, and the end behavior is stated here. Okay. What is the least possible now? We have to look at other features in the graph. So we have, for example, three turning points. As you can see, this is one turning point, decreasing then increasing. The second turning point, increasing then decreasing. And the third turning point, decreasing and then increasing. So we have three turning points. That means the graph should be of degree 4 or more. which is the number of turning point plus 1, because number of turning point should be 1 less than degree. Okay, maximum number of turning point. Now we have 3 zeros as well, which are the x-intercepts. Okay, so the degree must be at least 4. Here are the x-intercept. This is an x-intercept, which is a 0. This is another x-intercept, and the other is another. So we have 3 x-intercepts and 3 turning points. That means the degree must be at least 4. Okay. Okay, we go to part B. Locate the zeros and the multiplicity. Assume all of the zeros are integral values. That means they are integers. So the x-intercept of the graph are the zeros. So we can read from the graph -6 and this point. This is the value of the x value here is -6. Look at the scales. It goes in 2s, 4, 6, 8, -4, -6, -8, and -2. That's another one, and 4. This one. These are the x-intercepts and these are the zeros. The x-intercept is the 0. The question suggests that they are integers, so that's why I took -6, -2, and 4 integer values. Okay, so there is no decimal. Right. What is the multiplicity of these zeros? -6, -4, and -2 and 4. So we need to find the multiplicity. At -6, the graph crosses the x-axis and changes its position from above to below the x-axis. As you can see, this is above the x-axis. This is below the x-axis. So it crosses and changes the position. Okay. Right. What does it mean? This means that the sign of the function changes. Okay. So at -6, the function takes the value 0 and changes its sign. That means the multiplicity must be odd. Okay, so here is the sign positive at this point, or this set of points. Okay, so the y is positive, which is the function is positive, and below the x-axis the y is negative. That means the function takes the sign negative. That's why we say change the sign. So the multiplicity is odd. This is a rule. If you change the sign, the multiplicity is odd. Same happens with 4. Okay, it crosses and changes the position. That means the multiplicity is odd because the function changes its sign. Okay. Now, in at -2, this point here, it's a 0 of multiplicity even. Why? Because the graph is tangent to the x-axis. No change in sign of the function. Okay, the sign is always negative, and the x-axis. So this is the first part on deciding on the multiplicity. So we have -6 and 4 multiplicity odd and -2 even. The total of this multiplicity must be 4. Why? Because the polynomial is of degree 4, as we said. Okay, so it has a maximum of 4 zeros. So this point is a 0 and the other one is a 0. This one counts at 2 because multiplicity is 2. Okay, so -6 multiplicity odd, which is 1, and 4 multiplicity odd 1, and -2 multiplicity equals to 2. Okay, so the total is 2 plus 1 plus 1 equals 4. So we are done with the zeros and the multiplicity. We go to the next part, part C. We need to find the function that fits this graph. Okay, from the zeros and the multiplicities, we can write the function on the form, this form: x plus 6 multiplicity 1, so power 1, x minus 4 multiplicity 1, and x plus 2 multiplicity 2. From the multiplicity, you put the power. A is the leading coefficient that we need to find. So we need to find the value of the leading coefficient. Okay. For this, we use the remaining information, which is the point, the given point. We didn't use it in the problem. So we're going to use this point. Okay, 2 and negative 128. That means f of 2 equals negative 128. 2 is x and negative 128 is f of x, which is f of 2. Okay, That's your y. F of 2 is the y coordinate, right? So we substitute in the function with x equals 2. Okay, so 2, 2, 2. You plug 2 everywhere there is an x. So you get your function on this form after substitution. F of 2 equals, after substitution, yes, just substitute x with 2. Just a simple substitution. After that, you just do a calculation. Okay, so 2 plus 6 is 8, and 2 minus 4 is negative 2, and 2 plus 2 is 4 with the square. Calculate and simplify, you get this. Okay, all this gives you negative 256. Next step, divide by negative 256 each side. Okay, divide by negative 256, and you get the value of a equals half. So it is left, we only need to plug a there. Okay, so we substitute a with the value half, and we get our function on this form. That's it. We are done, and this is the end of this story. Thank you for watching, and see you soon with another video.